In October of 2019, a team of physicists at Google published a paper in Nature describing a result that should have stopped more people in their tracks than it did. Their quantum processor, a 53-qubit device called Sycamore, solved a specific mathematical problem in 200 seconds. The best classical supercomputer on Earth at the time would have needed somewhere between 2.5 days and 10,000 years to do the same thing, depending on who you asked and how generous you were with the estimate. Even the most conservative interpretation of that gap, 2.5 days against 200 seconds, is a factor of over 1,000. The more generous interpretation is a factor of over 150 million. Those numbers tell you something, but they do not tell you the most important thing. The most important thing is not how fast the machine was. It is why it was fast. And the answer to that question is one of the strangest things that working physicists have had to accept in the last century. The machine was fast because it was not computing inside a single universe. It was coordinating calculations across multiple versions of reality simultaneously and collecting the result. That is not a metaphor. It is not a popular science simplification of a more complicated idea. It is the explanation that the theoretical foundations of quantum computing actually point to, taken seriously by the people who built the field. And if it is true, then in October of 2019, humanity operated a device that reaches beyond the boundary of everything we can observe and measure. The machine is still running. Somewhere, right now, inside a refrigerated chamber cooled to temperatures colder than anything that exists naturally in the observable universe, it is doing it again. The person who first described why this had to be possible was not working at a major research laboratory. He was working alone at night in his house in Oxford, England, where he still lives and still rarely leaves. His name is David Deutsch, and in 1985, he published a paper that almost nobody read at the time. The paper did not propose an engineering solution to an existing problem. It asked a deeper question. Is there a physical machine that could, in principle, simulate any physical process in the universe? Not model it, not approximate it? Simulate it exactly, using the actual laws of physics as the operating system. The answer Deutsch arrived at was not what people expected. A classical computer cannot do this, not because it is too slow, not because we have not built one large enough. A classical computer operates inside a single physical reality, and that single physical reality does not contain enough resources. The universe we can observe and measure does not have enough room to hold all the calculations that a genuine universal simulator would need to perform. So where does it do them? Deutsch's answer, written plainly in that 1985 paper, is that the calculations happen across multiple versions of reality simultaneously, not as a philosophical position, as a physical mechanism. The quantum computer is the first device in human history that requires the existence of parallel worlds in order to function, and it functions. There is a number that makes this concrete. Consider a quantum computer with 300 qubits. The number of simultaneous states it can hold is 2 raised to the power of 300. Written out, that is a 2, followed by 90 zeros. That number is larger than the total count of atoms in the observable universe. Every atom, in every star, in every galaxy we have ever detected, mapped, or theorized about. A 300-qubit machine has more computational space than all of it combined. You cannot fit that computation inside one universe. There is simply not enough physical room. This is not a philosophical argument. It is a counting argument. If you need to work with more states than your universe contains particles, you are by definition using resources from somewhere beyond your universe. Deutsch looked at this arithmetic and drew the only logical conclusion he could find. The computation happens across parallel versions of reality, many instances of the same machine, each exploring a different path through the solution space, combining their results through interference into a single answer that arrives back here. The quantum computer is not a faster calculator. It is a device that coordinates work across multiple realities and returns the result to ours. And we built one. To understand what that means, you need to go back to 1935, when a physicist named Erwin Schrödinger sat down to write what he believed was a devastating critique of quantum mechanics. He was not trying to contribute to the theory. He was trying to break it. Quantum mechanics had been producing experimental results of extraordinary precision, but it contained an idea that Schrödinger found philosophically unbearable. The idea was that a particle does not have a definite state until it is measured. Before measurement, it exists in a combination of all possible states at once. Schrödinger thought this was absurd, so he constructed a thought experiment designed to make that absurdity visible. A cat, a steel box, a radioactive atom. If the atom decays, a mechanism triggers, and the cat dies. If it does not, the cat lives. Quantum mechanics says the atom is in both states simultaneously until observed. Therefore, Schrödinger argued, the cat must be simultaneously alive and dead until you open the box. He meant it as a trap, as proof that something in the theory had to be wrong. What happened instead is that physics kept confirming the theory, decade after decade, experiment after experiment, with greater and greater precision. The cat argument did not break quantum mechanics. It became its most famous illustration. A qubit, the basic unit of a quantum computer, works exactly like the atom in Schrödinger's box. It is not a zero. It is not a one. It is both simultaneously until the moment you measure it. And while it holds that superposition, it performs calculations across all its possible values at once. That is not the speed of the machine. That is its fundamental nature, not faster processing of a single thread of computation. Computation across multiple states simultaneously before collapsing into a single answer. The question this raises, and that almost nobody asks out loud, is this. If a qubit is genuinely in both states at the same time, what is it doing between measurements? What is happening in that space between the question and the answer? And if this is not a simplification, if the qubit is literally in multiple states at once, what does that say about the nature of reality in the moments when we are not observing it? The mechanism that makes the computation productive rather than chaotic was described by Richard Feynman in 1982, before the first quantum computer existed. Feynman suggested that the only way to efficiently simulate quantum physical systems was with a machine that itself operated by quantum rules. Embedded in that suggestion was an idea about how such a machine would actually use its quantum nature. The mechanism is interference. Think of two waves on the surface of water moving toward each other. Where the peaks of both waves meet, they add together and produce a higher peak. Where a peak meets a trough, they cancel each other out and the surface goes flat. Quantum systems do the same thing, but with probability. A quantum computer is engineered so that all the computational paths leading to wrong answers cancel each other out, like a peak meeting a trough. And all the paths leading to the correct answer reinforce each other, like two peaks combining. The machine does not try every possible answer and then check which one is right. It is structured so that the wrong answers destroy themselves through interference before the calculation is finished. What arrives at the end is not a lucky guess. It is what survives after everything incorrect has been systematically eliminated by the physics of the computation itself. Think about what that means. The machine is not selecting the right answer. It is creating conditions where wrong answers cannot survive, which raises a question about the nature of computation at a deeper level. Is this how reality works more broadly? Is the physical world we experience the result of a similar process where most possible configurations cancel out and only certain stable patterns survive long enough to be observed? And if so, what does it mean that we built a machine that deliberately replicates that process? Are we computing, or are we doing something closer to what the universe already does to produce reality in the first place? The man who provided the theoretical framework for why this all worked was not supposed to have his idea taken seriously. Hugh Everett III was a graduate student at Princeton in 1957 when he submitted his doctoral dissertation. The dissertation proposed what he called the many worlds interpretation of quantum mechanics. The basic idea was this: when a quantum system is measured and appears to collapse from a superposition into a single outcome, that collapse does not happen because one outcome is selected and the others disappear. All outcomes happen. Reality branches. Every possible result occurs in its own version of the universe. The cat is alive in one branch and dead in another. Both branches are equally real. There is no collapse. There is only multiplication. The physicist Niels Bohr, who at that time was the most powerful voice in the entire field, dismissed the idea. The community followed Bohr. Everett's dissertation was accepted, but his interpretation was treated as a curiosity at best. He left academic physics almost immediately after receiving his degree. He went to work for the Pentagon doing mathematical modeling for nuclear targeting strategies. He drank heavily. He smoked constantly. He died of a heart attack in 1982 at the age of 51, largely forgotten by the field he had tried to contribute to. His daughter Liz wrote in her diary that she wanted to die and meet her father in a parallel universe. His son Mark became a rock musician and named his band Eels. The many worlds interpretation that Bohr dismissed in 1957 is now, depending on who you ask, the leading theoretical framework for understanding why quantum computers work at all. The computation that cannot fit inside one universe fits because Everett was right. There are other branches, and Deutsch built a machine that uses them. What does it mean that the idea the entire physics establishment rejected for 30 years turned out to be an engineering requirement? What does it say about how we evaluate ideas that arrive before we have the tools to use them? And what does it tell us about ourselves that we built a machine requiring his mathematics without the mainstream conversation ever fully reckoning with what that implies? There is a question hiding behind all of this that the engineer in the laboratory does not have time to ask, but the physicist cannot stop asking. If the parallel worlds are real enough to compute inside, why do we not see them? Why does the world around us look like one single stable reality instead of a constantly branching fog of overlapping possibilities? Why does the cat appear to be either alive or dead the moment we open the box instead of both? The answer is called decoherence. A quantum system stays in superposition only as long as it remains isolated from everything around it. The moment it interacts with even a single particle from the outside environment, the superposition begins to collapse. Not because of any mystical act of observation, not because a conscious mind looked at it, simply because information about the system leaked out into the surrounding world. The environment, the air molecules, the photons bouncing around, the vibrations in the walls, they all constantly brush against quantum systems. And each interaction carries away a tiny piece of information. And once information leaks out, the superposition dissolves. The system picks a state. The branches stop being accessible to each other. This is why your coffee cup does not exist in superposition. It is interacting with trillions of particles every second. Its quantum information bleeds into the environment so fast that any superposition it might have had collapses before it could ever be measured. The macroscopic world looks classical and stable because decoherence happens almost instantaneously at the scales we live at. But here is what decoherence means for the engineering challenge. To keep a qubit in superposition long enough to actually compute with it, you have to isolate it from everything perfectly. The machines Google and IBM build are cooled to temperatures colder than deep space, precisely because heat is just particles moving, and moving particles interact, and interactions cause decoherence. The entire engineering challenge of quantum computing is essentially this: keep the computation hidden from the universe long enough to get an answer, which raises a question that is genuinely strange to sit with. If the computation is happening across parallel branches of reality while it is isolated, and then collapses into a single answer the moment it touches our world, what exactly is happening in those branches during the calculation? Is something occurring there that we will never have access to? And if we are deliberately hiding our most powerful computations from the observable universe, what does that say about the relationship between knowledge and observation? The Google supremacy experiment in 2019 was the first data point on a curve that very few people have looked at steadily. But the curve has a shape, and the shape matters more than any individual point on it. 53 qubits in 2019, 1,121 qubits in 2023. The number of qubits in leading processors grew by a factor of more than 20 in 4 years. That rate of growth is not linear. It is not even cleanly exponential in the way Moore's law described transistor growth. It is faster than the projections most quantum computing researchers were making in 2015. Every exponential curve looks manageable at the beginning. The first few doublings are small. You go from 1 to 2 to 4 to 8, and it seems linear, seems controllable, seems like something you can track and prepare for. And then somewhere in the middle of the curve, the numbers stop feeling like numbers and start feeling like something else entirely. 15 doublings from 53 qubits is approximately 1.7 million qubits. Most estimates place the threshold for breaking RSA 2048 encryption somewhere between 1 million and 4 million physical qubits, depending on error correction requirements. The arithmetic is a rough triangulation, not a firm prediction. But rough triangulations have a way of becoming more precise as the data points accumulate. What does the curve look like at doubling 20? And who is watching that curve most carefully right now? In 1994, a mathematician named Peter Shor worked out something that most of his colleagues had assumed was impossible. He wrote an algorithm, a set of instructions that a quantum computer could follow to break apart any large number into the prime numbers that multiply together to produce it. On the surface, that sounds like an abstract mathematical exercise. The connection to everything becomes visible the moment you understand how the internet works. Almost all of the encryption that protects the modern world, the layer of mathematics that keeps your bank account separate from everyone else's, that keeps private communications private, that protects the infrastructure of governments and militaries and hospitals and power grids, is built on a single assumption. Multiplying two large prime numbers together is easy. Working backwards from the result to find those original primes is practically impossible. Not theoretically impossible, practically impossible, meaning it would take a classical computer so long, thousands or millions of years, that the encrypted information would be worthless long before the lock was broken. That assumption is the foundation. Shor's algorithm removes it. A sufficiently powerful quantum computer running Shor's algorithm could factor those large numbers not in thousands of years, but in hours, possibly minutes. The entire cryptographic architecture of the modern world, built over 50 years, assumes that this reversal is not feasible. Shor proved that it is feasible. The machine just does not exist yet at the scale required to do it. But the machines are growing exponentially. And this is where the abstract becomes uncomfortably concrete. Everything encrypted today is potentially being stored by anyone with the resources to store it: governments, private actors, anyone waiting for the moment when the machine becomes powerful enough to open it. The term people in cryptography use for this is harvest now, decrypt later. Collect the locked data today and wait. The lock will eventually open. We have known about this vulnerability since 1994, 30 years, and the fundamental architecture of internet encryption has not changed. There is a particular institutional signal that is easy to miss if you are not looking for it. Not a press release, not a headline. A government agency quietly spending 8 years and significant resources solving a problem that officially does not yet exist. In 2016, the National Institute of Standards and Technology in the United States launched a competition. They invited mathematicians and cryptographers from around the world to submit new encryption algorithms, not better versions of existing ones, fundamentally different ones, built on mathematical problems that a quantum computer running Shor's algorithm could not break. 82 teams from 25 countries submitted proposals. The competition ran for 8 years. The final standards were published in 2024. Think about what this sequence actually communicates. A government body does not spend 8 years and coordinate 82 international teams to solve a hypothetical problem. They do not publish binding standards for a threat that exists only in theory. The implicit message inside the entire structure of that competition is this: the people with access to classified information about the state of quantum hardware believe the threat is real, is coming on a timeline that requires action now. The systems that need to be updated to use those new standards, the actual infrastructure of the internet, banking, government communications, will take years more to retrofit, which means there is a window. A gap between when the quantum machines become capable enough to break current encryption and when the new encryption is actually installed everywhere. How long is that window? Who knows exactly how wide it is? And who right now is paying very close attention to its edges? There is a second algorithm that deserves as much attention as Shor's, but rarely gets it. In 1996, a researcher named Love Grover published a procedure for quantum accelerated search. Imagine an unsorted list of 1 billion items, and you are looking for one specific item. A classical computer has to check items one by one. On average, it will find the item after checking 500 million of them. Grover's algorithm finds the item in roughly 30,000 checks. Not because it moves faster through the list, but because it uses quantum interference to amplify the probability of the correct answer and suppress the probability of all incorrect answers simultaneously. Every wrong item cancels itself out. The right item reinforces itself. The machine does not search. It creates conditions in which everything that is not the answer becomes invisible. Now think about what search means at scale. Every database that has ever been built, every password that has ever been created, every pattern hidden inside any collection of data. What kinds of hidden structure exist in the world that we have not yet found because our search tools were too slow? What patterns are embedded in physical reality, in biological systems, in the history of the universe, that become visible only when you can search at quantum speed? The thing that Einstein invented as an argument against quantum mechanics became a tool inside quantum computers. Quantum entanglement. Two particles interact and then fly apart in opposite directions. Quantum mechanics says that certain properties of these particles are not determined until measured. But it also says that once you measure one particle, the other instantly takes on a complementary value, no matter how far apart they are. Measure the spin of particle A and find it pointing up, and particle B will instantly be found pointing down. Instantly, regardless of whether B is across the room or on the other side of the galaxy. Einstein called this spooky action at a distance. He found it not just strange, but physically impossible. Nothing can travel faster than light. If measuring one particle instantly affects another across any distance, that seems to require either that information travels faster than light, which Einstein's own relativity forbids, or that the particles were carrying hidden predetermined information from the start, values that just looked random until measured. Einstein preferred the second explanation. He was sure quantum mechanics was incomplete. He was wrong, not probably wrong. Experimentally, measurably, definitively wrong. The physicist who settled the question was a 34-year-old Frenchman named Alain Aspect. He worked at the Institut d'Optique outside Paris. In 1982, he created pairs of entangled photons and sent each photon flying in opposite directions toward detectors. At the last possible moment, while the photons were already in flight, he randomly switched the orientation of the detectors. This last-minute switching was crucial. It closed a loophole that earlier experiments had left open. If the detectors had fixed orientations, a skeptic could argue that the photons had somehow learned the settings before they left and encoded that information in their hidden variables. By switching after the photons were already traveling, Aspect made that explanation physically impossible. The results came back unambiguous. The correlations between the two photons exceeded Bell's limit. Not slightly, clearly. Einstein's hidden variables cannot explain what Aspect measured. The universe is not locally real in the way Einstein assumed. Two particles can be separated by any distance and remain connected in a way that has no classical explanation and no classical parallel. The Nobel Prize in Physics in 2022 went to Aspect, together with John Clauser and Anton Zeilinger, for this work 40 years after the experiment. Physics moves carefully when the implications are large enough. What Aspect proved is not just that quantum mechanics is correct. He proved that the world is structured in a way that our everyday intuition about separation and distance and independence simply does not apply at the fundamental level. Two things can be arbitrarily far apart and still be, in some physically meaningful sense, one thing. In 2013, two of the most respected theoretical physicists alive published a paper with a title that looked like an equation, ER equals EPR. The ER refers to Einstein and Rosen, who in 1935 described a theoretical connection between two black holes, a tunnel through spacetime, now called a wormhole, or an Einstein-Rosen bridge. The EPR refers to Einstein, Podolsky, and Rosen the same year, the same Einstein, describing quantum entanglement. Juan Maldacena and Leonard Susskind were proposing that these two phenomena, wormholes and entanglement, are not just analogous. They are the same thing. When two particles are quantum entangled, they are connected by a microscopic wormhole in spacetime. The non-local connection that Einstein called spooky action at a distance is spooky because it is literally a geometric connection through a layer of reality that exists beneath the space we move through. Entanglement is not a strange correlation between distant objects. It is a bridge, a physical structure in the geometry of spacetime, connecting two points that appear separate when measured from the outside. If this is correct, and it has not been refuted, and it has generated an enormous amount of productive theoretical work, then the entanglement that quantum computers use as a computational resource is not just a property of particles, it is a property of space-time itself. The computer is not exploiting a quirk of quantum statistics. It is using the geometric structure of reality, the actual shape of space-time, as a computational medium, which means that when a quantum computer creates and manipulates entangled qubits, it is in some physically meaningful sense creating and manipulating tiny structures in the geometry of space. John Wheeler spent 60 years at the center of theoretical physics. He coined the term black hole. He worked with Bohr on nuclear fission. He supervised the doctoral dissertations of Richard Feynman and Hugh Everett. By the time he reached the end of his career, he had spent more time thinking seriously about the foundations of physical reality than almost anyone alive. And the conclusion he arrived at was this: information is not something that the universe contains. Information is what the universe is made of. He called it from bit. Every particle, every field, every physical thing that exists gets its existence, its properties, its reality from answers to yes or no questions. Does the electron spin up or spin down? Did the photon pass through the left slit or the right? Wheeler argued that the physical world is not the primary thing with information layered on top of it. The information is primary. The physical world emerges from it. This is a genuinely strange idea to sit with, because it inverts the intuition most of us carry around without examining it. We tend to think of reality as the solid ground, and information as something we extract from it, like harvesting wheat from a field. Wheeler is saying the field is made of wheat all the way down. There is nothing underneath the information. Now, bring that idea into contact with a working quantum computer. If the universe is made of information, then a device that manipulates information at the most fundamental physical level is not modeling reality. It is not simulating reality. It is operating on the actual substrate from which reality is constructed. Every calculation a quantum computer performs is an intervention in the informational fabric of the universe itself. 30 years before Wheeler published his framework, a physicist named Rolf Landauer at IBM had already provided the experimental grounding that Wheeler's intuition required. In 1961, Landauer published a paper arguing that information is not abstract. It is physical. When you erase a single bit of information, you release heat. Not metaphorically, literally. The act of taking a system that holds a 1 or a 0 and resetting it to a known state releases a tiny but measurable and theoretically unavoidable amount of thermal energy into the surrounding environment. This became known as Landauer's principle. In 2012, a team led by physicist Eric Lutz built an experiment delicate enough to actually measure it. They trapped a single microscopic particle in a laser-generated well, manipulated it to erase one bit of information, and measured the heat released. The result matched Landauer's formula. Thinking, at the most fundamental level, generates heat, not because computers are inefficient and produce waste, but because erasing information is physically irreversible, and irreversibility has a thermodynamic cost that cannot be designed away. Every thought has a price. Every calculation leaves a physical trace in the universe. Some researchers have suggested that quantum computers operating in superposition may approach a kind of reversibility that classical computation cannot achieve, potentially sidestepping some of Landauer's heat cost. If that is true, then quantum computation is not just faster, it is operating closer to the theoretical minimum energy cost that physics allows. It is computing in a way that is more aligned with how the universe itself processes information than anything we have built before. In 1973, American mathematician Charles Bennett had already been working on the thermodynamics of computation and would later clarify that reversible computation generates no heat at all. The connection between information, heat, and physical reality is not a philosophical footnote. It is one of the deepest threads in modern physics, and quantum computers sit right at its intersection. The fragility of qubits was the argument most physicists used in the 1980s and early 1990s to believe that practical quantum computers were physically impossible. A single stray photon, a tiny vibration, a temperature fluctuation smaller than anything you could feel. Any of these can destroy a quantum superposition before the calculation is finished. and a destroyed superposition gives you a wrong answer. Classical computers handle errors through redundancy. Store the same information in 3 places, and if one copy gets corrupted, the other 2 outvote it. But you cannot do this with qubits. Quantum mechanics has a rule called the no-cloning theorem, which says it is physically impossible to make an exact copy of an unknown quantum state. You cannot back up a qubit the way you back up a file. In 1995, Shor, the same person who wrote the encryption breaking algorithm, solved this second problem as well. He figured out how to protect quantum information without copying it. The key insight was to encode one logical qubit across 9 physical qubits in a way that spreads the information through the relationships between them rather than storing it in any single one. If one physical qubit gets disturbed, the logical information survives in the correlations between the remaining 8. The information was never in one place, it was in the structure. What followed from Shor's error correction scheme was a theoretical result called the threshold theorem, which showed that if the error rate per physical qubit is kept below a certain threshold, you can build arbitrarily large and reliable quantum computers by adding more physical qubits per logical qubit. The machine can be made as reliable as you need it to be. This was the moment when quantum computing shifted from a theoretical curiosity to an engineering project. In February of 2024, Microsoft announced something the quantum computing community had been waiting for and arguing about for nearly 2 decades. They had created a topological qubit, not a faster qubit, not a more connected qubit. A qubit protected from errors by the geometry of space itself. Classical error correction builds walls, more redundancy, more physical qubits backing up each logical one. Topological protection is different. It encodes information not in any single particle, but in the global shape of a quantum system, in properties that can only be disturbed by something that alters the entire structure at once, not by any local noise or stray particle. The particles Microsoft used to achieve this are called Majorana fermions. They are particles that are their own antiparticles, a property that means the information they carry has no single location. It exists in the relationship between particles that can be physically separated. Ordinary environmental noise cannot corrupt what has no fixed address. The theoretical foundation for what Microsoft built was laid by a Russian physicist named Alexei Kitaev in 1997. Kitaev was working on a question most of his colleagues considered premature. How do you build a quantum computer that is fundamentally protected from errors rather than corrected after they occur? His answer came from topology, the branch of mathematics that studies properties of shapes that do not change when you deform them continuously. A coffee cup and a donut are topologically identical because each has exactly one hole, and you can reshape one into the other without tearing. Topological properties are robust by definition. You cannot accidentally change how many holes something has by poking it slightly. Kitaev proposed encoding quantum information in topological properties of physical systems. Information stored this way inherits the robustness of topology itself. Local disturbances simply cannot reach information encoded in a global geometric property. They are the wrong kind of perturbation. It is like trying to change the number of holes in a donut by painting it a different color. The operation does not connect to the property you care about. What Kitaev showed is that physics contains natural structures, where information and geometry are the same thing. And what Microsoft showed in 2024 is that those structures can be built in a laboratory. There is a problem underneath quantum computing that sits deeper than hardware. In 2016, a computer scientist named Thomas Vitek published work examining a fundamental question: can a classical observer ever verify the output of a quantum computation? The answer he arrived at was uncomfortable. In general, no. If a quantum computer gives you a result and you want to check whether that result is correct, the verification process itself requires computational resources that grow exponentially with the size of the original computation. For any sufficiently large quantum computation, classical verification is not just difficult, it is physically impossible within any reasonable time or resource budget. We are building machines whose outputs we cannot independently check, not because we lack engineering sophistication, because the laws of physics make checking harder than computing, exponentially harder. We trust the machines because we tested them on small problems, where we could verify the answers by other means, and we assume that trust extends to large problems where we cannot. That assumption may be correct, but it is an assumption. We are building an infrastructure of trust around systems that are by their fundamental nature not fully auditable by the civilization that built them. In 2020, a group of mathematicians posted a paper online that took 2 years for the broader mathematical community to fully verify. The result was so unexpected that several leading researchers initially assumed there must be an error somewhere. The paper proved something called MIP star equals RE. What it showed is that two entangled quantum computers can convince a classical observer of the correctness of solutions to problems that are in a precise technical sense beyond the reach of any classical verification system whatsoever, including problems that classical computers cannot even be guaranteed to solve in finite time. The implications unsettled even the researchers who proved it. It means that quantum entanglement adds something to the landscape of what can be known and verified that has no classical equivalent and no classical upper bound. There are truths that two quantum entangled systems can demonstrate to a classical observer that the classical observer could never reach independently. What does it mean that the boundary of what can be proven has shifted depending on what kind of physical system is doing the proving? Stephen Hawking spent the last 40 years of his life wrestling with a related question. Can information be destroyed? In 1974, he proved mathematically that black holes are not the permanent objects they appear to be. They slowly radiate energy, a process now called Hawking radiation, and over vast timescales they shrink and eventually vanish. The radiation they emit appears to be completely random. It carries no information about what fell in. A library could fall into a black hole, and the radiation that eventually comes out would look identical to the radiation from a black hole that swallowed only hydrogen gas. If that is true, the library is gone. Not transformed, not encoded somewhere, gone. This created what physicists call the black hole information paradox. On one side, Hawking insisting that information is lost and quantum mechanics needs to be revised. On the other side, almost everyone else in the field insisting that information cannot be destroyed and that Hawking's calculation must be missing something. In 2004, Hawking publicly conceded. He announced at a conference in Dublin that he had been wrong, that information is preserved somehow, and he paid off a bet he had made with the physicist John Preskill by giving him an encyclopedia. But the how of information preservation in black holes remains genuinely open. Nobody has a complete answer. And the reason this connects directly to quantum computing is this. If information is always conserved, always recoverable in principle, then every quantum computation leaves a permanent physical trace in the universe. Nothing computed is ever truly erased. What does it mean that every calculation we have ever run still exists somewhere in the structure of reality? And what does it mean that we do not know where? In 1969, the German engineer Konrad Zuse published a small book called Calculating Space. Zuse was not a marginal figure. He had built the first programmable computer in history, the Z3, in his parents' living room in Berlin in 1941, while the city was being bombed. He understood computation as well as anyone alive. And at the end of his career, he proposed something his colleagues mostly set aside as philosophical wandering. He proposed that the universe is a computation. Not that it resembles a computation, or that it can be modeled as one. That it is one. That physical reality is the output of a discrete computational process running on some substrate we cannot directly observe. Every particle interaction is a computational step. Every physical law is an algorithm. For 30 years, this was treated as a curiosity. Then the physics of information developed enough that the question stopped being philosophical and started being physical. Zuse's idea, once considered a charming eccentricity, turns out to be a legitimate scientific hypothesis with testable consequences. Stephen Wolfram spent a decade writing a 1,200-page book that he published in 2002 called A New Kind of Science. The reception from the physics community was mixed, but the central idea has proven more durable than its critics expected. Wolfram's argument was built on a simple observation about cellular automata, grids of cells that follow simple rules about what state each cell should be in based on its neighbors. Rule 110, one of the simplest possible sets of instructions, produces patterns of extraordinary and apparently unlimited complexity. Wolfram proposed that the fundamental laws of physics might be exactly this, not complicated equations governing a continuous reality. Simple rules applied repeatedly to a discrete structure, generating the apparent complexity of the physical world as an emergent property. Quantum mechanics in this picture is not a fundamental theory. It is what simple computational rules look like when observed from inside the system that is running them. The randomness and superposition are features of the perspective, not features of the underlying process. Why do we assume that the correct description of reality must be continuous rather than discrete? Why do we assume that the laws of physics are given rather than generated? And what would change in our understanding of quantum computers if the universe they operate inside is itself a computational process running on something simpler than we have imagined? Max Tegmark is a physicist at MIT who published a paper in 2007 and later a book proposing what he calls the mathematical universe hypothesis. The idea goes further than Wheeler's it from bit. Tegmark proposes that the universe is not described by mathematics. It is a mathematical structure. Everything that mathematically exists physically. There is no separate physical world that mathematics describes. The mathematics is the thing. If reality is a mathematical structure, then a device that manipulates mathematical relationships at the fundamental physical level is not computing about reality. It is computing inside reality as part of its structure, with access to the same substrate that reality itself is made of. The distinction between the quantum computer and the physical world it operates in begins to dissolve. And if that is true, then the limit on what a quantum computer can compute is not set by our engineering. It is set by the limits of mathematics itself, which brings in a result from 1931 that Tegmark's framework makes newly strange. Kurt Gödel proved that any mathematical system powerful enough to describe basic arithmetic contains true statements that cannot be proven within that system. If the universe is a mathematical structure, it contains truths that cannot be derived from within it. There are facts about reality that reality itself cannot compute. What does a quantum computer do when it approaches one of those edges? In 2006, Seth Lloyd at MIT published a calculation that puts a hard number on something that had previously been discussed only in qualitative terms. He calculated the computational capacity of the observable universe. The answer he arrived at is approximately 10 to the power of 120 operations performed over the entire history of the cosmos, using every particle and every interaction as a computational resource. Every electron, every photon, every quark performing its quantum interactions is, in Lloyd's framework, executing a computational operation. The universe is not like a computer. It is one. It has been running a single program since the Big Bang, using every physical interaction as a step in the calculation. Now place our quantum computers inside this picture. We are building devices that operate on the same physical principles as the universe's own computation. They use the same quantum mechanical rules, the same entanglement, the same superposition, the same interference. They are not modeling the universe's computation from outside. They are participating in it, adding their operations to the total, becoming in a small but physically real sense part of the universe's ongoing calculation. If the universe is computing something, and we add our own quantum computation to that process, do we change the output? Is the trajectory of the universe's calculation altered by what we compute inside it? In 1935, Albert Einstein co-authored a paper with Boris Podolsky and Nathan Rosen that was intended to bury quantum mechanics. The paper described quantum entanglement, and Einstein called it spooky action at a distance. He intended this as a criticism, a sign that the theory must be missing something. What Einstein could not have known was that 80 years later, engineers would be harvesting his supposed absurdity as a computational resource. In the summer of 2017, a team of Chinese physicists used a satellite called Micius to conduct a quantum encrypted video call between Beijing and Vienna. The distance was approximately 7,600 kilometers. The call lasted 75 minutes. The encryption was guaranteed by the laws of quantum mechanics rather than by mathematical complexity. This was not a demonstration in a controlled laboratory. It was a real communication between real cities on opposite sides of the planet, protected by a physical law rather than a mathematical assumption. The security of quantum key distribution does not rest on computational difficulty. It rests on the fact that measuring a quantum system disturbs it. You cannot observe a quantum state without affecting it. If anyone intercepts the quantum-encoded key, the act of measurement necessarily disturbs the quantum states. The disturbance shows up as errors. The two parties detect the presence of the eavesdropper by checking their error rates. The eavesdropper gets nothing useful and reveals themselves in the attempt. The symmetry here is remarkable. The same physics that makes quantum computers capable of breaking classical encryption also provides the only kind of encryption that is provably permanent. The universe handed us the lock and the skeleton key at the same time. The question is simply which one gets used first. China has since announced plans to expand quantum communication infrastructure, a quantum internet, one where communications are secured not by computational hardness, but by physics, is being built. Not planned, built. What does the internet look like when its physical layer is quantum rather than classical? What becomes possible on a network where the connections between nodes are maintained by entanglement? And who controls the satellites that hold those connections together? In 2003, a philosopher at Oxford named Nick Bostrom published a paper that made an argument so simple it fits in 3 sentences. Either almost all civilizations at our level of development go extinct before reaching the technological maturity to run detailed simulations of their ancestors, or almost all technologically mature civilizations have no interest in running such simulations. Or we are almost certainly living in a simulation right now. This is not a thought experiment. It is a probability argument. If even one technologically mature civilization exists and has any interest in simulating its history, the number of simulated beings in the universe vastly outnumbers the beings in base reality, which means that any randomly selected conscious observer is vastly more likely to be simulated than real. The argument has a clean logical structure and no obvious flaw. Here is where quantum computers change the weight of that argument. For decades, simulating a universe with genuine quantum behavior would have required resources proportional to the quantum state space being simulated, which, as we established, is astronomically large, larger than the number of atoms in the observable universe. But a quantum computer does not simulate quantum behavior classically. It runs it. A sufficiently powerful quantum computer could simulate quantum mechanical systems exactly because it is itself quantum mechanical. The computational barrier that made perfect simulation seem physically impossible weakens as quantum machines grow. What does it mean to build the tool that makes the simulation hypothesis not just plausible, but practically achievable? And if we are living inside a computation, what happens to the computation when a sufficiently powerful computer is built inside it? In the summer of 1950, Enrico Fermi was having lunch with colleagues at Los Alamos. The conversation drifted toward the general question of extraterrestrial life. Fermi, who had a habit of doing quick calculations in his head, suddenly asked a question that seemed casual but was not. Where is everybody? The universe is approximately 13.8 billion years old. It contains somewhere between 200 billion and 2 trillion galaxies, each with hundreds of billions of stars. The fraction of those stars with planets in habitable zones is not small. The time it would take a civilization with even modest technological capability to spread across the entire galaxy, even without faster-than-light travel, is measured in millions of years, which is a blink in cosmic time. So if life and intelligence arise with any reasonable frequency, the galaxy should be full of signals, full of megastructures, full of evidence, and it is not. The sky is quiet. Fermi's question has generated dozens of proposed answers in the 70 years since that lunch. But here is the one that the arc of everything we have discussed points toward. What if the silence is not absence? What if the most advanced civilizations are not in space? What if they are inside computation, inside simulated realities of their own construction, inside quantum systems that offer more richness and complexity than the physical universe that spawned them? What if the reason we do not hear anyone is that everyone who reaches a sufficient level of technological development eventually builds the door that leads inward and walks through it? In 1989, the mathematician and physicist Roger Penrose published a book called The Emperor's New Mind. The argument at its center was this: human consciousness cannot be computational in the classical sense, because human mathematicians can recognize the truth of certain statements that no classical algorithm can prove. Penrose was drawing on Gödel's incompleteness theorems. His conclusion was that the brain must be doing something that classical computers cannot do, and the only physical process he could identify that might account for this was quantum mechanics. Working later with anesthesiologist Stuart Hameroff, he proposed that quantum computations occur inside structures called microtubules inside neurons, and that consciousness arises from this quantum processing in a way that is fundamentally non-algorithmic. The hypothesis remains deeply controversial. Most neuroscientists find it unlikely. Most quantum physicists find the brain too warm and wet for quantum coherence to survive long enough to matter. But the controversy is scientifically legitimate rather than philosophically dismissible. If Penrose is even partially right, then the boundary between quantum computation and consciousness is not a boundary at all. The brain may already be a quantum computer. We may have been running quantum computations for as long as minds have existed. What we are building in refrigerated chambers may not be something alien to human experience. It may be a crystallized, engineered version of what thinking already is. And if that is true, what does it mean to build a machine that thinks more powerfully than we do by the same physical mechanism we use to think at all? David Deutsch does not fly on airplanes. He rarely leaves Oxford. He works at night. He has described himself as someone who finds it easier to think about abstract structures of reality than to navigate the practical requirements of ordinary social life. He is also, by most accounts of people who work in quantum computing, one of the 2 or 3 people most responsible for the fact that quantum computers exist as a field of inquiry at all. His 1985 paper laid the theoretical architecture. He has continued pushing at the same question from different angles for 40 years. What I find striking about Deutsch is not the eccentricity, which is common enough among theoretical physicists, but the completeness of his conviction. He genuinely believes that the many worlds interpretation is correct, not as a working assumption, not as a useful framework, as a description of actual reality. He believes that when a quantum computer runs, the computation happens across a vast number of parallel versions of the universe simultaneously, that those parallel instances are as real as this one, that the machine is genuinely reaching into that parallel structure and extracting answers. And the machine he helped design works. It gives correct answers. It outperforms classical computers on problems that can be independently verified. If the machine works, and the only coherent explanation for why it works requires parallel universes, what exactly is the reasonable position to hold about parallel universes? And what does it mean that the man most responsible for the machine has held that position quietly from a house in Oxford for 40 years? We started with a number, 200 seconds against 10,000 years. A gap so large, it seemed like a measurement error rather than a physical fact. But it was not an error. It was a data point. And every data point we have examined since has pointed in the same direction. The machine works because it borrows resources from parallel versions of reality. Deutsch showed this in 1985, and the machines confirm it every time they run. Information is the primary substance of the universe. Wheeler spent 60 years arriving at this conclusion, and Landauer proved it has a measurable physical cost. The boundary between computation and reality is not a boundary at all. Zuse intuited this in 1969. Wolfram formalized it in 2002. Tegmark extended it in 2007. Lloyd calculated it in 2006. Everett died not knowing his mathematics would become an engineering requirement. His idea was dismissed as too strange to be useful and turned out to be too fundamental to avoid. The machines are growing. 53 qubits in 2019, 1,121 in 2023. The curve does not flatten on its own. The encryption that protects modern civilization was designed before Shor, published in 1994, and has not fundamentally changed since. The quantum internet is being built in orbit. What scientists still do not know is extensive. They do not know the precise timeline for cryptographically relevant quantum computation, though the institutional preparations are treating it as a near-term problem rather than a theoretical one. They do not know how to reconcile quantum mechanics with general relativity, and quantum computers may eventually provide experimental access to that boundary. The ER equals EPR connection between entanglement and geometry remains unproven at a foundational level, though it continues to generate productive theoretical work. The question of whether the Penrose-Hameroff proposal about quantum processing in biological neural tissue is correct remains open, and a sufficiently powerful quantum computer might one day help us test it. The holographic principle, which states that all information inside a volume is encoded on its surrounding surface, connects quantum information theory to black hole physics in ways that researchers are still working to fully understand. And the question of whether the universe itself is a computation, in the precise technical sense, is no longer purely philosophical. It has acquired testable implications that quantum experiments may eventually be able to probe. What is most striking about the current moment is not any single experiment or any individual result. It is the convergence. Wheeler from information theory, Landauer from thermodynamics, Zuse from computation, Wolfram from complexity, Tegmark from mathematics, Lloyd from physics, Everett from quantum foundations, all pointing at the same cluster of ideas from different directions, arriving at the same strange conclusion that computation, information, and reality are not three separate things. Underneath all of it sits a question we have been circling for this entire conversation without quite landing on directly. We built a machine that works by interacting with parallel versions of reality. We do not know what those interactions look like from the other side. We do not know what a computation looks like in the branches that contribute to our answer and then go unused. We have never asked whether the act of quantum computation has consequences in the parallel instances it draws from. We have never asked because we assumed those instances were not real enough to matter. But the whole point, the entire foundation of why the machine works, is that they are real. They are real enough to compute with, which makes them real enough to wonder about. The machine is running right now, somewhere in a refrigerated chamber, pulling answers from places we cannot see. The curve is still climbing. The questions are getting heavier. And whoever is watching the frontier most carefully is not necessarily the one making the most noise about it. If you found this worth your time, the best thing you can do is share it with someone who would ask the same questions. Like this video and subscribe so you do not miss what comes next in this series. The next piece goes deeper into what the machines are already being used for, and the answer is stranger than most coverage suggests. There is a dimension to the Google Sycamore result that almost never makes it into the public coverage. The specific problem Sycamore solved was called random circuit sampling. It was not chosen because it was important on its own. It was chosen precisely because it is easy for a quantum machine and hard for a classical one. That choice was deliberate. It was the cleanest way to demonstrate a genuine gap between what quantum hardware can do and what classical hardware can do under fair conditions. The problem involves generating outputs from a random quantum circuit and verifying that the output distribution matches the expected quantum mechanical distribution. Classical computers can check individual outputs, but generating the full distribution from scratch requires simulating the entire quantum state, which requires classical memory that scales exponentially with the number of qubits. IBM's counterargument that with enough classical disk storage the problem could be solved in roughly 2.5 days was technically legitimate, but it highlighted something important. Classical simulation of quantum circuits requires trading time for space. You can make the simulation faster by using more memory. IBM was proposing to use an enormous amount of classical memory to compress the timeline from 10,000 years to 2.5 days, which still left a factor of over 1,000, and that factor grows as the circuit depth increases. The more complex the quantum operation, the harder it becomes to find classical shortcuts through memory expansion. The Sycamore result was not the end of the story. It was the first sentence of a much longer document. The public argument between Google and IBM over quantum supremacy ran for years and generated significant coverage, most of which focused on who was right about the specific numbers. Google said 10,000 years. IBM said 2.5 days. Both numbers have been revised since. But the argument itself, the visible public disagreement between two of the largest technology companies in the world, contains a signal that is more important than either company's preferred headline. When two organizations with strong incentives to claim leadership in a field argue publicly about the size of an advantage rather than whether an advantage exists, you are looking at a consensus wearing the costume of a dispute. Nobody at IBM argued that Google's machine showed no quantum advantage. Nobody at Google argued that IBM's challenge was technically baseless. They argued about magnitude. That argument is evidence of how fast the field is moving and how much both companies understand to be at stake. The organizations that are not arguing publicly, the ones we do not hear from because their work is classified or because they have chosen not to announce results, are the ones worth thinking about most carefully. The public frontier of any technology is almost always behind the actual frontier. The gap varies by field and by how much incentive there is to keep progress quiet. In quantum computing, some of the most significant potential applications, breaking encryption, securing communications, modeling physical systems relevant to weapons development, are exactly the applications where the incentive to be quiet is highest. What is the actual frontier? How far behind the public announcements are the classified programs? The history of nuclear weapons research is instructive here. The Trinity test in 1945 was the first public demonstration of a weapon that had been in development for 3 years, involving tens of thousands of people, at a cost in today's terms of over $20 billion. None of it was publicly known before the demonstration. The technology went from theoretical to operational in 3 years without anyone outside the program knowing it was happening. The analogy is not exact, but the general principle applies. Technological developments with strategic military implications do not reliably appear in press releases before they appear in capabilities. The quantum computing landscape may have invisible layers that the public conversation does not capture. The D-Wave situation in 2013 introduced another kind of problem that has only become more pressing as the machines have grown. D-Wave sold quantum processors to Lockheed Martin for approximately $10 million and to a joint Google and NASA program for comparable amounts. Physicists then argued publicly about whether the machines were actually doing anything quantum. Papers were published on both sides. The results were ambiguous. Some benchmarks showed quantum behavior, others did not. Some problems it solved faster than classical computers, others it solved slower. By 2015, the consensus had settled into something unsatisfying. D-Wave machines show some quantum effects, but whether those effects are responsible for their computational behavior is genuinely unclear. A company had sold machines worth tens of millions of dollars to some of the most technically sophisticated organizations in the world, and nobody could definitively say what the machines were doing internally. This is not a story about fraud. D-Wave was not lying. It is a story about something more structurally strange. We had entered a regime where the behavior of a physical system was too complex to verify by any classical means available to us. The machine was operating in a space that our tools could not fully illuminate. And this was before quantum computers became genuinely powerful. The verification problem grows as the machines grow. A quantum computer with 53 qubits operates in a Hilbert space, a mathematical space of quantum states, with dimension 2 raised to the power of 53. That is approximately 9 quadrillion dimensions. Classical computers can still, in principle, simulate a system of this size, though it requires enormous resources. The Sycamore result pushed this to the edge of what is classically tractable. Beyond a certain threshold, classical simulation becomes physically impossible, not slow, physically impossible within the lifetime of the universe. When the machines cross that threshold for general computation rather than specially chosen benchmark problems, we will have no independent way of checking what they tell us. Think about the implications for scientific discovery. If a quantum computer computes the folding structure of a novel protein and reports that the structure binds to a specific disease target with high affinity, we cannot independently verify that computation through any classical means once it involves enough qubits. We can run the experiment to check the prediction, but we cannot audit the reasoning. The machine becomes an oracle. We can test its outputs against reality, but we cannot examine its logic. This is not necessarily fatal. We use classical computers as oracles for calculations we cannot do by hand all the time. But the scale of the difference is new. A classical computation we trust because we understand the algorithm and can, in principle, trace every step. A sufficiently large quantum computation is trustworthy only in the sense that a physical experiment is trustworthy. We can replicate its outputs, but we cannot follow its internal reasoning. What does it mean for the institutions that govern knowledge and decision-making when a central tool of discovery operates in a regime that is not fully auditable? And what frameworks do we need to build, not just technically, but institutionally and epistemologically, for a world in which some of the most important calculations being performed cannot be independently checked? The question of what quantum computers will discover, as opposed to what they will compute, is one that is only beginning to be asked seriously. Drug discovery is the obvious near-term application. Protein folding, which the classical AI system AlphaFold addressed with remarkable success for many classes of proteins, is only one layer of the molecular biology that determines how drugs work. Simulating the quantum mechanical interactions between a drug molecule and its target requires capturing electron correlations, solvent effects, and conformational dynamics at a level of accuracy that classical computers cannot achieve without dramatic simplification. Quantum computers operating at sufficient scale will be able to run these simulations without simplification. The implications for pharmaceutical development are significant. A large fraction of drug development failures, some estimates suggest the majority, happen at late-stage clinical trials after enormous investment because the molecular behavior predicted by simplified classical models turns out to be different from the actual molecular behavior in a biological context. More accurate quantum mechanical simulation of molecular interactions could shift this failure rate earlier in the pipeline when failures are much cheaper. It could also reveal mechanisms that classical simulation misses entirely, opening therapeutic pathways that have not been considered because the required molecular detail was computationally inaccessible. Materials science is another domain where quantum simulation offers something qualitatively different rather than merely quantitatively faster. High-temperature superconductors, materials that conduct electricity without resistance at temperatures achievable without expensive cooling equipment, remain poorly understood after decades of research. A room-temperature superconductor would transform energy transmission, computing hardware, and transportation. Nitrogen fixation, the industrial process that produces fertilizer and underpins modern agriculture, currently consumes approximately 1 to 2% of all global energy, because the catalyst required to break the nitrogen triple bond runs at high temperatures and pressures. The enzyme nitrogenase in certain bacteria accomplishes the same reaction at room temperature and ambient pressure. Understanding the quantum mechanical mechanism of how nitrogenase works, accurately enough to design a synthetic equivalent, requires precisely the kind of quantum simulation that classical computers cannot perform at sufficient resolution. These are not speculative long-term applications. They are problems where the limiting factor is computational, where the physics is understood well enough to specify what the calculation requires, and where quantum computers at sufficient scale provide what is needed. The timeline to sufficient scale for these applications is the subject of significant debate among researchers, but the direction is not. In 1993, 6 physicists published a paper that demonstrated quantum teleportation as a theoretical procedure. The title sounds like science fiction. The content contains no fiction. The procedure they described allows the complete quantum state of a particle to be transferred from one location to another without moving the particle itself. Not the particle, the information that defines it. Every quantum property that makes it what it is, transferred completely. The procedure requires 3 things: a pair of entangled particles shared between sender and receiver, a classical communication channel operating at or below the speed of light, and the original particle whose state you want to transfer. The sender performs a measurement linking the original particle to their half of the entangled pair. They send the result of that measurement through the classical channel. The receiver uses that result to perform an operation on their half of the entangled pair. At the end of the procedure, the receiver's particle is in exactly the quantum state that the original particle was in. The original particle no longer holds that state. It has moved. In 1997, Anton Zeilinger performed the first experimental demonstration of quantum teleportation in a laboratory. In 2017, a Chinese team used the satellite Mixius to teleport a quantum state from a ground station in Tibet to the satellite orbiting 1,400 kilometers overhead. The distance is almost beside the point because entanglement does not weaken with distance. But it matters as a demonstration that this is not a laboratory curiosity confined to a controlled room. It works at the scale of the planet. Quantum teleportation does not move matter. It moves the information that defines quantum states. And if Wheeler is right that information is the primary substance of reality, then quantum teleportation is not moving a description of something. It is moving the thing itself, leaving behind an empty shell. What does it mean that we can relocate the informational identity of a physical object while leaving its physical substrate behind? Is the object the matter, or is it the information? And if it is the information, what are we when we are moved? The holographic principle, developed through work by Gerard Hooft and Leonard Susskind during the 1990s, adds another layer to this. Imagine a region of space, any region, a sphere with a defined volume. The holographic principle states that the maximum amount of information that can be contained inside that sphere is not determined by its volume. It is determined by the area of its surface. The information capacity scales with the surface area, not the volume. All the information describing everything that happens inside the volume is somehow encoded on the two-dimensional surface surrounding it. The interior is not the primary thing. The boundary is. This is not a philosophical suggestion. It emerged from rigorous calculations about black holes and thermodynamics. The principle has since become one of the most productive frameworks in theoretical physics, connected to string theory, to the nature of black holes, to quantum gravity. If the three-dimensional world inside a volume is fully described by a two-dimensional surface, then space itself may be a kind of projection. Not an illusion exactly, but something more like a derived object, something that emerges from a more fundamental layer of information encoded elsewhere. Which means that when a quantum computer manipulates information at the most fundamental physical level, it may be operating at a layer of reality that is more basic than space itself, not inside space, underneath it. If space emerges from information, what else emerges from information that we have been treating as foundational? The question of quantum teleportation and the holographic principle converge in the ER=EPR proposal from Maldacena and Susskind. If entangled particles are connected by microscopic wormholes, and if the holographic principle tells us that information is the more fundamental layer from which geometry emerges, then quantum teleportation involves something stranger than information moving from one place to another. It involves information traversing a connection that may be more fundamental than the space that appears to separate its endpoints. What we call distance may be a coarser description of a finer geometric structure that entanglement gives us direct access to. And if quantum computers create and manipulate entangled states at scale, they are not just exploiting the geometry of spacetime as a computational resource. They are, in some sense, that we do not fully understand, sculpting it. The no-cloning theorem, the rule that you cannot make an exact copy of an unknown quantum state, has an implication that goes beyond the engineering problem it creates for quantum error correction. Classical information can be copied freely. Everything about the classical information economy, libraries, the internet, broadcasting, backup systems, depends on the fact that you can copy a bit without destroying the original. Quantum information cannot be copied this way. The quantum state of a particle is destroyed the moment it is perfectly transferred to another particle. This is not a limitation of our technology. It is a fundamental feature of how quantum information works. The no-cloning theorem is not a practical obstacle. It is a law. What this means is that quantum information has a kind of irreducible individuality that classical information does not have. There is only one copy of a quantum state. If it is transmitted, it moves. If it is measured, it is altered. If it is teleported, it disappears from its origin. In a world where information is the primary substance of reality, the fact that quantum information is fundamentally non-duplicable raises questions that go beyond cryptography and computation. Identity, in the sense of a unique configuration that persists over time, is a property of quantum systems in a way that has no classical analog. Whether this is relevant to consciousness, to biological individuality, to anything beyond physics, is entirely open. But it is a feature of the informational substrate of reality that we have barely begun to think through. The connection between quantum mechanics and time is another thread that quantum computers pull at. Classical computation is fundamentally asymmetric with respect to time. Information processing has a direction. You take an input, you produce an output. If you try to run the computation backwards, you generally need more information than the output contains to recover the input. This is why erasing information generates heat. Erasure is an irreversible operation. You cannot reconstruct what was erased from the heat that was generated. Quantum mechanics, at its fundamental level, is time symmetric. The laws of quantum mechanics work identically forwards and backwards in time. There is no arrow of time built into the fundamental equations. The arrow of time that we experience, the sense that past is fixed and future is open, emerges from thermodynamics, from the direction of increasing entropy, from the statistical tendency of systems to evolve toward higher probability configurations. But at the quantum level, every process is, in principle, reversible. Quantum computers can, in principle, perform computations that are genuinely reversible, generating no heat from the logic operations themselves. This was the theoretical insight that Bennett worked out in the 1970s. A computation that is reversible leaves no thermodynamic trace. It does not commit to a direction. And if a sufficiently advanced quantum computation could exploit this reversibility systematically, it would be operating in a regime where the ordinary constraints of thermodynamics do not apply in the usual way. We are far from achieving this in practice. But the theoretical possibility is real, and the engineering push toward lower error rates and longer coherence times is, among other things, a push toward more reversible computation. The relationship between quantum computing and time becomes stranger when you consider closed time-like curves. General relativity permits, in principle, configurations of spacetime where a path through spacetime can loop back on itself, creating the possibility of travel into the past. These are closed time-like curves. Physicists have debated for decades whether they are physically realizable or whether some mechanism, perhaps quantum gravity, prevents them. In 2009, a physicist named David Deutsch, the same Deutsch who wrote the 1985 paper on quantum computation, published a paper analyzing what quantum computers would be able to compute if closed time-like curves existed. The result was striking. A quantum computer with access to even a single closed time-like curve could solve problems that are computationally intractable without one, problems that sit in complexity classes well above what any ordinary quantum computer can access. Whether this is relevant to anything physical is deeply uncertain, but it illustrates how deeply quantum computation is entangled with the fundamental structure of spacetime. The practical implications of quantum computing for artificial intelligence are beginning to receive serious attention. Classical machine learning is computationally expensive in specific ways. Training large neural networks requires enormous matrix multiplications and optimization over high-dimensional parameter spaces. Quantum computing offers potential speedups for certain classes of these operations. Quantum amplitude estimation provides quadratic speedups for sampling problems. Quantum linear algebra algorithms offer potential exponential speedups for specific matrix operations. The question of whether these speedups survive the overhead of preparing quantum states from classical data, a process that often washes out theoretical quantum advantages, is actively being worked on. But the theoretical possibility is clear. A sufficiently powerful quantum computer could, in principle, accelerate machine learning in ways that compound the capabilities of both technologies simultaneously. The combination is something to think carefully about. A quantum computer that can perform Grover search on enormous datasets, combined with a learning system that can identify and exploit patterns in those datasets, combined with a quantum simulation capability that can model physical and chemical systems with unprecedented accuracy, and combined with quantum communication infrastructure that is physically unhackable, describes something that looks qualitatively different from any tool we have built before. Not because any individual component is magic, but because the combination creates capabilities that do not exist in the parts. The race to build this is global and serious. The United States, China, the European Union, the United Kingdom, Japan, Canada, and Australia all have national quantum technology programs. China's investment has been particularly substantial and sustained. The Mauritius Satellite Program, the Quantum Key Distribution Network connecting major Chinese cities, the domestic production of superconducting quantum processors. These represent a coordinated national effort rather than isolated research initiatives. The United States programs, both classified and public, have accelerated significantly since the National Quantum Initiative Act was signed in 2018. What happens when two major powers both have cryptographically relevant quantum computers within a few years of each other? The existing framework of nuclear deterrence, which has provided a kind of stability for 70 years, rests on the assumption that neither side can destroy the other's second strike capability without receiving an unacceptable retaliatory blow. A large fraction of the communication systems that coordinate those second-strike capabilities are encrypted using algorithms that quantum computers will eventually break. The transition period, the window between when one side achieves cryptographically relevant quantum computation and when the other side has retrofitted its communications to quantum-resistant encryption, is a window of strategic vulnerability that military planners are certainly modeling. How that window is managed will be one of the more consequential policy questions of the next decade. The ethics of quantum computing is a domain that has received much less attention than the technology itself. The capability to break current encryption is one dimension, but the capability to search vast datasets at quantum speed, to model molecular interactions in biological systems at atomic resolution, to verify mathematical proofs that classical systems cannot check, to simulate quantum mechanical systems relevant to weapons design, all of these raise questions about access, governance, and the relationship between technological capability and political power that are not being answered as quickly as the technology is advancing. Who should have access to cryptographically relevant quantum computers? If such a machine existed today and only one nation possessed it, the strategic implications would be extraordinary. The communications of every other nation's government, military, and financial system would be readable. The question of whether quantum computing capability becomes a form of strategic dominance comparable to nuclear weapons is not settled. The comparison is imperfect in important ways, but the imperfection of the comparison does not mean the strategic question is not real. The quantum internet, if it is built to global scale, partially addresses this by providing quantum-secured communication that is resistant to quantum decryption. But the infrastructure for quantum communication, the satellites, the fiber optic networks capable of carrying quantum states, the ground stations, requires massive investment that will not be uniformly distributed. The nations and entities that build and control that infrastructure will have significant leverage over who benefits from quantum-secured communication and who does not. The distribution of the technology may matter as much as the technology itself. None of these questions have obvious answers. They are presented here not as predictions, but as the predictable shape of the problems that the technology creates. We have a habit, as a civilization, of building powerful tools and then figuring out their governance afterward. Nuclear weapons, social media, genetic engineering, all followed this pattern. The cost of the afterward varies, depending on how long it takes and what happens during the delay. Quantum computing is still in the early phase where governance frameworks are being built before the full capability arrives, which is genuinely unusual. The NIST competition for post-quantum cryptography is an example. Whether the frameworks being built are adequate to the full range of challenges the technology creates is a different question. The deepest question that quantum computing raises is not technical. It is philosophical, and it is one that we cannot answer, but also cannot afford to ignore. If the many worlds interpretation is correct, and the machines we are building depend on it being correct, then every time a quantum computer runs, something happens in the parallel branches that contribute to its answer. We do not know what that something is. We have not asked whether the branches that are used and then discarded in a quantum computation are affected by having been used. We have treated the many worlds as a resource, the way early industrialists treated rivers as a resource, without asking what effects their use might have. This is not an argument that quantum computation is harmful. It is an observation that we are operating machinery whose full physical implications we do not understand, and that the physical implications in question concern the structure of reality itself. That seems like the kind of thing that deserves more attention than it has received. Hugh Everett believed that his death was not an ending, but a branching. That some version of him continues in some branch of reality, watching the technology built on his mathematics become the most consequential engineering project of the 21st century. Whether that belief was comfort or delusion is not answerable. But the mathematics he left behind is not delusion. It is not comfort. It is an engineering requirement, and the machines that require it are running. There is a subtlety in how quantum computers actually deliver their speed advantage that is worth understanding precisely because the popular descriptions often get it slightly wrong in ways that matter. Quantum computers are not faster at everything. They are not a universal accelerator for all computation. There are specific problem types where quantum algorithms deliver advantages, and the nature of those advantages varies. Shor's algorithm for factoring large numbers provides exponential speedup over the best-known classical algorithms. The factoring problem that takes a classical computer years to solve takes a quantum computer hours or minutes. That gap grows as the numbers get larger. Grover's algorithm for unstructured search provides quadratic speedup. If a classical computer needs 1 trillion steps to find a needle in a haystack of 1 trillion items, a quantum computer needs approximately 1 million steps. That is a substantial advantage, but not an exponential one. For some problems, quantum computers provide no advantage at all. A quantum computer programmed to run a classical algorithm is simply a very expensive classical computer with many operational disadvantages. The implication is that the quantum advantage is domain-specific. Understanding which domains it applies to and to what degree is one of the central tasks of quantum algorithm research. The field has identified clear quantum advantages in simulation of quantum systems, factoring and discrete logarithms via Shor's algorithm, unstructured search via Grover's algorithm, linear algebra operations via quantum linear systems algorithms, and sampling from certain probability distributions. The applications being developed for near-term quantum hardware tend to cluster in these domains. Drug discovery exploits quantum simulation. Financial optimization exploits quantum sampling. Pattern recognition in certain data types exploits quantum linear algebra. The combination of domains where the advantage is real and the problems where the advantage translates into practical value is the space that the engineering and research communities are actively mapping. One domain that is drawing increasing attention is quantum machine learning, where the intersection of quantum algorithms and learning systems creates possibilities that neither technology offers alone. Classical machine learning has transformed what is possible with data, but it operates within the constraints of classical computation. Certain operations that are bottlenecks in classical learning algorithms, matrix inversion, sampling from high-dimensional distributions, finding optimal solutions in complex landscapes, have quantum speedups in specific formulations. Whether those speedups survive, the practical constraints of near-term quantum hardware is actively being researched. But the theoretical case for quantum-enhanced machine learning is increasingly solid, and the experimental demonstrations are beginning to appear. The connection between quantum computing and the fundamental question of what computation itself is runs through a history that predates quantum mechanics. Alan Turing published his foundational paper on computable functions in 1936, defining the concept of a universal computing machine and establishing the limits of what classical computation can solve. The Church-Turing thesis, developed in parallel by Turing and Alonzo Church, proposed that any physically realizable computation can be simulated by a Turing machine. For decades, this was treated as a fundamental constraint. Then, quantum mechanics became well understood enough that people started asking whether it was actually true. Deutsch's 1985 paper was directly addressing the Church-Turing thesis. He was asking whether the thesis needed to be reformulated in explicitly physical terms, as a claim about what physical processes can compute, rather than what abstract computational models can compute. His answer was that a quantum Turing machine, a Turing machine operating by quantum rules, is strictly more powerful than a classical one. The quantum Church-Turing thesis, which Deutsch proposed, says that any physically realizable computation can be simulated by a quantum computer. This is a strictly stronger claim than the classical version, because quantum computers can simulate quantum mechanical systems exactly, while classical computers cannot. Whether the quantum Church-Turing thesis is true, whether there exist physically realizable computational processes that even a quantum computer cannot simulate, is still an open question. But the fact that the classical version needed revision at all tells you something important about the relationship between computation and physics. The limits of what can be computed are not abstract mathematical facts. They are facts about the physical universe. The energy landscape of quantum computing is worth attending to as the technology scales. The machines built today require enormous cooling infrastructure. Dilution refrigerators that maintain the operating temperature of quantum processors consume substantial electrical power. The processors themselves operate at temperatures near absolute zero, roughly 15 millikelvin, which requires removing all thermal energy from the system continuously. A quantum data center operating at scale would have cooling requirements comparable to a small power plant. This is not a permanent constraint. The engineering of cryogenic systems is improving, and some modalities of quantum computing, notably photonic and room temperature trapped ion systems, Avoid the extreme cooling requirements of superconducting qubits. But the energy economics of quantum computing are a real constraint on near-term deployment, particularly for applications that require continuous operation of large-scale systems. The transition from laboratory demonstrations to deployed infrastructure raises questions of fault tolerance at a scale that has not yet been addressed experimentally. The threshold theorem tells us that fault-tolerant quantum computing is theoretically achievable if error rates are kept below a certain threshold. Current hardware is approaching those thresholds but has not yet crossed them for all relevant error types. The specific threshold depends on the error correction code used, the physical connectivity of the hardware, and the nature of the dominant error channels. Google, IBM, and Microsoft are each pursuing somewhat different architectural approaches to fault-tolerant quantum computing, reflecting genuine uncertainty about which approach will scale most effectively. The architectural competition is not just an engineering race. It is an experiment to determine which physical systems best support the specific error correction requirements of large-scale quantum computation. The question of what happens when the machines become fault-tolerant at scale is one that most people outside the field have not yet had to engage with seriously. We tend to think of technological transitions as gradual. In the case of quantum computing, the transition from classically tractable to classically intractable computation, from a machine that can be checked to a machine that cannot, is a threshold that will be crossed at some specific moment. Before that moment, quantum computers are powerful tools with verifiable outputs. After it, they are oracles. The institutional, legal, and scientific frameworks for operating in a world with unverifiable quantum oracles do not exist yet. Building them requires deciding, as a society, what kinds of decisions we are willing to delegate to systems we cannot fully check. That is not primarily a technical question. It is a question about trust, governance, and the distribution of knowledge and power that deserves more public deliberation than it has received. The long arc of this history, from Schrödinger's thought experiment in 1935 to Google's result in 2019 to the quantum internet being built in orbit today, is not a simple story of progress. It is a story of ideas dismissed and then vindicated, of consequences running far ahead of understanding, of a technology that emerged from attempts to describe reality more accurately and is now forcing us to reconsider what reality is. Everett's many worlds dismissed and then resurrected as an engineering requirement. Einstein's spooky action dismissed and then repurposed as a computational resource. Zeuss's computational universe dismissed and then returned as a legitimate scientific hypothesis. The pattern repeats. The ideas that arrive before the world is ready for them have a way of becoming unavoidable when the tools to test them finally exist. What has not changed is the underlying phenomenon. The machine that computes in superposition across states that cannot be held in a single universe. The entanglement that connects particles across any distance. The interference that eliminates wrong answers by physics rather than by checking. These are features of reality that were there long before we built anything to exploit them. We did not create quantum mechanics. We discovered it. The machines we are building are not imposing something new on the universe. They are learning to operate at a layer of the universe that was always there, beneath the classical world we experience, more fundamental than the space and time we navigate, constituted from information in ways that we are only beginning to trace. The refrigerated chambers will keep getting colder. The qubit counts will keep climbing. The algorithms will keep extending into new domains. The questions about what this means will keep getting harder to avoid. And the man in Oxford will keep working at night, thinking about parallel worlds that are real enough to compute inside, having never needed to fly anywhere to do it. The way that interference works in a quantum computer is worth examining more carefully, because it is the mechanism that separates a quantum computer from a device that merely tries every answer at once and picks the right one. That description, which appears in many popularizations, is misleading in a way that obscures what makes the machine genuinely remarkable. When a quantum computer enters superposition across many states, it is not running separate computations in parallel that then report back independently. It is running a single quantum process in which all possible computational paths coexist in superposition. The art of quantum algorithm design is in structuring that quantum process so that the paths leading to correct answers constructively interfere with each other, while the paths leading to incorrect answers destructively interfere and cancel out. The machine does not receive a message from parallel universes saying, "We found the answer." It is structured so that the answer is the only thing that survives the interference process. This is why quantum algorithm design is so difficult, and why quantum computers are not simply better at all problems. Designing a quantum algorithm requires finding a way to encode the problem so that the interference structure amplifies correct answers and suppresses incorrect ones. This is possible for some problems and not obvious or achievable for others. The class of problems where efficient quantum algorithms are known is much smaller than the class of all problems. Finding new quantum algorithms, new ways of exploiting interference to solve important problems faster, is one of the central challenges of theoretical computer science. Shor's algorithm accomplishes this using the quantum Fourier transform, a quantum version of the classical algorithm for computing Fourier transforms that runs exponentially faster on a quantum machine. The structure of the factoring problem, specifically the periodicity that underlies the relationship between a number and its prime factors, makes it amenable to this approach. The quantum Fourier transform extracts the period of a function across all possible inputs simultaneously through interference, and the period is the key to finding the prime factors. The elegance of Shor's algorithm is in how it transforms an apparently intractable arithmetic problem into a question about periodicity that the quantum Fourier transform can answer efficiently. Grover's algorithm works differently. Rather than transforming the problem, it iterates a process called amplitude amplification. The algorithm starts with a uniform superposition of all possible answers, and then repeatedly applies an operation that slightly increases the probability amplitude of the correct answer and slightly decreases the probability amplitude of incorrect answers. After approximately square root of n iterations, where n is the number of items being searched, the correct answer has been amplified to near certainty and can be extracted by measurement. The elegance here is in the iterative structure. No single step resolves the search. The answer emerges from the cumulative effect of many small amplifications. The process is more like refining an estimate through repeated measurement than like looking something up. Both algorithms illustrate a general principle. Quantum computation does not bypass the need to do computational work. It organizes that work so that physics does the selection, using interference to concentrate probability on correct answers. The universe, operating at the quantum level, is extraordinarily good at this kind of selection. Quantum computers are devices for harnessing that capability and directing it at specific problems. The scale at which this becomes practically significant varies by problem. For cryptographically relevant factoring, the machine needs to maintain coherence across thousands to millions of physical qubits for the duration of the computation, which is a formidable engineering challenge. For smaller-scale quantum simulation, the requirements are less extreme, and several groups have already demonstrated quantum advantage for specific simulation tasks on near-term hardware. The roadmap from where we are to where we need to be is not a single leap. It is a series of incremental engineering achievements, each extending the coherence time, reducing the error rate, increasing the connectivity, and scaling the number of qubits, accumulating toward a threshold that the theory tells us exists and that the engineering is steadily approaching. IBM has published a detailed quantum development roadmap that projects specific qubit counts and error metrics through the late 2020s. Google has made similar projections, though with less detail publicly. Both roadmaps project fault-tolerant operation at scales relevant to cryptographic applications within the current decade, conditional on continued progress in error correction. The conditional is important. Error rates have not decreased as fast as qubit counts have increased, and the two metrics are both necessary for fault-tolerant computation. The roadmaps represent aspirations informed by current progress, not certainties. But the aspiration is serious, and the funding and talent committed to achieving it are substantial. The geopolitical dimension of this race is not simply about which nation achieves cryptographic relevance first. It is about the entire ecosystem of quantum technologies, quantum sensing, quantum communication, quantum simulation, and quantum computing that will shape military and economic capabilities over the next several decades. Quantum sensors using entanglement to achieve measurement precision beyond classical limits are already being deployed for navigation, geological survey, and medical imaging applications. Quantum communication networks using quantum key distribution are operational in China and being built in Europe and the United States. The competition is not a single race to a single finish line. It is a broad competition across a technology landscape that touches sensing, communication, computation, and simulation simultaneously. The difficulty of predicting the trajectory of any of these capabilities is compounded by the classified nature of much of the most advanced work. What is publicly known about quantum hardware in 2026 almost certainly understates what exists in classified programs, following the historical pattern of technologies with clear strategic military applications. The gap between public knowledge and actual capability is probably not 10 years, as it might have been in the early days of nuclear weapons development. The technology is too broadly distributed and too deeply embedded in academic and commercial research for that kind of secrecy to be maintained. But a gap of 2 to 4 years between what is publicly known and what is operationally deployed in classified programs is entirely consistent with historical precedent and with the incentives that currently exist. All of this, the hardware race, the algorithm development, the cryptographic transition, the geopolitical competition, the philosophical implications, converges on the same underlying physical fact. The quantum world does not work the way the classical world works. It does not have the definiteness, the locality, the separability, the limited state space of classical physics. It is stranger, richer, and more deeply interconnected. We have been aware of this for a century. We have been building tools to exploit it for 40 years. We are only now reaching the scale where those tools begin to interact with the world in ways that matter outside the laboratory. The quantum computer does not change physics. Physics was always like this. It changes what we can do with physics, and the list of what we can do is still being written. The interference patterns that eliminate wrong answers in a quantum computation are the same physical phenomenon that produces the colors in a soap bubble, that creates the bright and dark bands in a double-slit experiment, that determines the energy levels of electrons in atoms. Interference is one of the oldest and most fundamental features of wave phenomena. Quantum mechanics reveals that it applies not just to water waves and light, but to probability itself. And quantum computers are devices for steering that fundamental feature of reality toward problems we want to solve. The strangeness is not in the machine. The strangeness was always in the reality the machine inhabits. The machine just makes it impossible to look away. The history of science contains several moments where a technology designed for one purpose revealed, almost accidentally, something fundamental about the structure of reality. The telescope was built to see farther. It revealed that Earth orbits the Sun and is not the center of the universe. The microscope was built to see smaller. It revealed that living organisms are made of cells and that disease is caused by organisms invisible to the naked eye. Particle accelerators were built to probe matter. They revealed that matter is mostly empty space and that the particles we thought were fundamental are themselves composite objects with complex internal structure. In each case, the technology did what it was designed to do, and in doing it made it impossible to maintain a picture of reality that had seemed adequate before. Quantum computers fit this pattern. They are being built to compute faster. And in working out how to build them, and in watching them operate, we have been forced to confront the reality that the universe has a structure that our classical intuitions simply cannot accommodate. The parallel branches required for Everett's many worlds to be the engineering foundation rather than the philosophical curiosity. The entanglement that Einstein dismissed as impossible, now serving as a practical computational resource. The informational substrate that Wheeler spent a career arguing for, now the framework within which quantum error correction and quantum communication operate. The holographic structure of space-time, which emerged from black hole thermodynamics, now connecting to the topology used in quantum error correction codes. The implications are not yet fully worked out. The connections are not all understood. But the direction they point is consistent, and the destination they approach is strange. We are learning, through engineering, that reality is not the solid, local, definite thing that everyday experience suggests. The classical world we navigate, the macroscopic world of coffee cups and cars and conversations, is an emergent phenomenon arising from a quantum foundation that is utterly unlike it. Decoherence is the mechanism that bridges the gap. The macroscopic world looks classical because quantum information bleeds into the environment so quickly that superpositions are destroyed before we can observe them. We live in the decoherent limit. Quantum computers are built to operate outside that limit, to maintain quantum coherence long enough to exploit the computational resources that the quantum foundation provides. And the resources it provides are extraordinary. The interference that eliminates wrong answers, the entanglement that creates correlations with no classical analog, the superposition that enables computation across many states simultaneously, the topological protection that stores information in geometric properties immune to local noise, the quantum Fourier transform that extracts periodicity from exponentially large superpositions. These are all features of the quantum foundation of reality. They were not designed for computation. They are features of how the universe works at its most fundamental level. Quantum algorithms are methods for channeling these features towards specific problems. The fact that some problems yield to quantum algorithms and others do not tells us something about the structure of those problems in relation to the structure of reality. The hardest conceptual shift required to understand quantum computing is not technical. It is the shift away from the intuition that a computer is doing something local and sequential, processing information step by step in a single thread of causality, toward the recognition that a quantum computer is doing something global and simultaneous, exploiting the entire informational structure of a quantum state in a way that has no classical analog. The classical analogy that works best is probably with music. A classical computer is like playing a melody, one note at a time. A quantum computer is like a chord, where the relationships between all the notes coexist simultaneously, and the interference between them determines what you hear. But even that analogy breaks down, because the chord is not just in our world. If Deutsch is right, the chord is being played across many worlds simultaneously, and what arrives in ours is the result that survives the interference across all of them. The music comes from somewhere we cannot hear directly. We only receive the note that remains after everything else has canceled out. Sit with that for a moment. A machine that operates by exploiting resources from parallel versions of reality, that uses the geometry of space-time as a computational medium, that manipulates the informational substrate from which physical reality is constructed. That can break the encryption, protecting the world's communications. That can simulate molecular systems with a precision inaccessible to classical computation. That may accelerate the discovery of materials and drugs that are not currently possible to design. That poses verification challenges that cannot be met classically. That is growing exponentially, following a curve whose later doublings we are poorly equipped to anticipate from our current position on it. This is the technology that is being built right now, in university laboratories and corporate research facilities and classified government programs, simultaneously, globally, rapidly. The people building it are engineers and physicists doing carefully defined experimental work. They are not, mostly, sitting with the full philosophical weight of what they are building. That is not a criticism. That is how science works. You focus on the tractable problem in front of you, and you let the implications take care of themselves for someone else to work out. But the implications are there. They were always there, in the quantum mechanics that has been sitting in the foundations of physics for a century. The quantum computer just makes them impossible to keep in the background. When you build a machine that requires parallel universes to function, the parallel universes stop being a philosophical footnote and become a practical fact about the world you live in. Everett knew this. Deutsch knew this. Wheeler spent a lifetime trying to communicate this. The machine is their vindication and our inheritance. What we do with it, how we govern it, how we think about what it implies for our understanding of reality and our place in it, is a question that belongs not just to physicists and engineers, but to everyone. Because everyone lives in the universe, whose structure the machine reveals. There is a specific experiment from 2022 that exemplifies how far quantum technology has come, from laboratory curiosity to engineered capability. Researchers at the University of Science and Technology of China demonstrated quantum key distribution over a distance of approximately 1,000 kilometers using a combination of satellite and ground-based infrastructure. The quantum states were maintained with sufficient fidelity to establish a secure key at that distance. The security was not computational. It was physical. The guarantee was not that an eavesdropper would need too long to break the encryption. It was that an eavesdropper could not intercept the key without disturbing the quantum states in a way that would be detectable. Compare that to classical key distribution. When two parties want to communicate securely using classical methods, they need to either meet in person to exchange keys or rely on a mathematical problem, like factoring large numbers, that is believed to be hard, but is not proven to be hard. The security of classical encryption is probabilistic and computational. It is secure as long as no one has a fast enough computer and no one finds a better algorithm. Quantum key distribution has security that is categorical and physical. It is secure because of how measurement works in quantum mechanics. No improvement in computing power changes this. No new mathematical insight breaks it. The gap between these two kinds of security is not a matter of degree, it is a matter of kind. Classical cryptographic security is a bet against the future. Quantum cryptographic security is a consequence of physics. For applications where the security requirements are long-term and the adversary has both resources and patience, the difference matters enormously. Medical records, diplomatic communications, critical infrastructure control systems, financial architecture, all of these have security needs that extend decades into the future. Classical encryption protecting any of these today will be vulnerable to a cryptographically relevant quantum computer whenever one is built. Quantum key distribution protecting these today is secure, regardless of what is built in the future. The practical obstacles to widespread quantum key distribution are real. Quantum states are fragile and cannot be amplified the way classical signals can. The distance over which quantum key distribution works is limited by the transmission losses in optical fiber and by the atmosphere. Satellites extend this range by operating above the atmosphere where transmission losses are lower for specific wavelengths of light. But building a global quantum communication network requires quantum repeaters, devices that can extend the range of quantum communication without the measurement that would disturb the quantum states and compromise security. Quantum repeaters require quantum memory, the ability to store quantum states for extended periods. Quantum memory is an active area of research that has not yet reached the performance levels required for a global network. The path from today's demonstrations to a global quantum internet involves solving these problems. The demonstrations prove the principle is sound. The engineering to make it scalable and cost-effective at global infrastructure level is the work of the coming decade or two. The investment in that work, both public and private, is substantial and growing. The quantum internet is not a speculation. It is an engineering project with identified challenges and funded research programs addressing each of them. The convergence of quantum computing, quantum communication, and quantum sensing is creating a technology landscape that is fundamentally new in ways that go beyond any individual capability. Quantum sensing uses entanglement and superposition to achieve measurement precision beyond classical limits. Atomic clocks using quantum effects are already the most precise timekeeping devices ever built, with applications in navigation, scientific measurement, and telecommunications. Quantum gravimeters using cold atoms can map the gravitational field of the Earth with precision sufficient to detect underground structures, aquifers, and mineral deposits. Quantum magnetometers can detect magnetic fields with sensitivity that enables new approaches to medical imaging and materials characterization. These sensing capabilities, combined with quantum computing to process the data they generate and quantum communication to securely transmit it, create possibilities that do not exist in any of the individual technologies alone. The medical applications of this convergence are beginning to be seriously explored. Brain imaging using quantum magnetometers sensitive enough to detect the magnetic fields produced by neural activity would provide resolution and information content beyond current methods. Quantum simulation of biological molecules would enable drug design at a level of accuracy that changes the economics and timeline of pharmaceutical development. Quantum machine learning applied to genomic and proteomic data might reveal disease mechanisms and drug targets that are invisible to classical analysis. Each of these individually is significant. Together, they describe a transformation of medicine that is not speculative about whether it is possible, but only about when. The same convergence applies to climate and environmental science. Quantum sensing enables measurements of atmospheric composition, ocean temperature, and ice coverage with precision not achievable classically. Quantum simulation enables modeling of atmospheric chemistry and climate dynamics at resolutions that classical supercomputers cannot reach. The combination could provide the scientific foundation for understanding and addressing climate change in ways that current tools do not permit. This is not an argument that quantum technology will solve climate change. It is an observation that the scientific questions underlying climate change, the ones about how physical and chemical processes in the atmosphere and ocean interact at molecular and global scales simultaneously, are exactly the kind of questions that benefit from the capabilities quantum technology provides. The acceleration of scientific discovery that quantum computing enables is itself a second-order effect that is hard to reason about clearly. Science builds on science. A discovery in molecular simulation enables a discovery in drug design, which enables a discovery in disease biology, which enables a discovery in medicine. The compounding effect of better tools on the rate of knowledge generation has been observed throughout the history of science, from the telescope and microscope to the mass spectrometer and the gene sequencer. Quantum computing and quantum sensing are tools of comparable transformative potential. The second-order effects of having them are effects on the rate at which the first-order effects are generated. We are at the beginning of that acceleration. What we are not at the beginning of is the underlying physics. The quantum mechanics that quantum computers exploit is a century old. The experiments confirming it are decades old. The theoretical frameworks connecting it to information, geometry, and computation have been developed over 60 years by some of the best minds in physics. The quantum computer is not a new discovery. It is the maturation of a long conversation between physics and mathematics about the nature of reality. What has changed is that the conversation has produced engineering. The abstract is becoming concrete. The theoretical is becoming operational. The philosophical is becoming physical. And physical things have consequences. The machine in the refrigerated chamber is not a thought experiment. It is not a paper calculation. It is a device that operates on the quantum structure of reality and returns results to the classical world. It is the first human artifact to do this at scale. Everything that follows from it, the encryption broken, the drugs designed, the communications secured, the scientific questions answered that could not be answered before, all follow from the same physical fact. The universe has a quantum layer. We learn to see it. Now, we are learning to use it. The questions that remain open are not small ones. Whether the many worlds interpretation is the correct foundation or whether some other interpretation of quantum mechanics will eventually prove more adequate. Whether the ER equals EPR correspondence between wormholes and entanglement is a deep truth about the structure of space-time or a useful mathematical analogy. Whether consciousness involves quantum processes in the way Penrose and Hameroff propose. Whether the universe is, in the precise technical sense, a computation. Whether the limits of what quantum computers can compute are set by the physical laws of our universe alone, or whether there is something, some structure beyond, that places constraints we have not yet discovered. These questions are not purely philosophical. Each of them has implications for what quantum computers will eventually be able to do, and how we should understand what they are doing when they do it. The answers, when they come, will not come from armchairs. They will come from experiments. From the machines growing in capability until they probe questions that could not previously be probed. From the moment when a quantum computation reaches a scale where its behavior cannot be predicted by any classical model, and we have to watch and measure and find out what actually happens. That is the situation we are moving toward. Not a situation of answers, but of better questions and the tools to pursue them. The refrigerated chambers will keep running. The qubits will keep accumulating. The algorithms will keep extending. And the universe, which has been quantum mechanical since the beginning, will keep being exactly what it always was. We are just catching up to it.